Hi everyone, I'm Mrs. Fitz, and I am going to be talking today about solving differential equations. All right, so let's jump right into it. We have the definition of a differential equation is essentially an equation that involves an unknown function, y equals f of x, and its first or higher derivatives. A solution to a differential equation is an equation of the form y equals f of x that satisfies the equation. The solution can either be a general or a particular solution. Now, you are looking for a particular solution, if you are given an initial condition. So they might say, find the solution to this differential equation given that f of 0 equals 6, right? Okay, the order of a differential equation is the order of its highest derivative appearing in the equation. A differential equation can be called linear if it can be written in the form a sub n of x times y to the nth power plus a sub n minus 1 of x times y to the n minus first power, blah, 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 blah. Actually, those are the nth derivative, sorry. So y to the nth derivative, y to the n minus first derivative, y prime all the way to y. Okay, so let's take a look at how to classify these. So here's some examples. Sometimes just looking at the general form doesn't make it quite as obvious. So if we have a differential equation, x squared times y prime plus e to the x times y is equal to 4, this is called a first order. And that's because the highest derivative is a first derivative. Is it linear or nonlinear? Well, in this case, this one would be linear because we have a function of x times y prime plus another function of x times y, which equals 4. So this would be considered a linear differential equation. Okay, the next one, this one, we have our highest derivative is just y prime. This would still be considered a first order. And this one is actually nonlinear, and that's because your y prime is being squared, right? It's a nonlinear derivative if you want to interpret it in that way. Okay, the next one, we have y double prime is equal to sine of x times y prime. This is a second order. That's because your highest derivative is the second derivative. And this one actually is linear as well because it can be written as a function of x times your derivative plus another function of x times your other derivative. You can actually rearrange the equation and make it look like that general form at the top. Okay, and then the last one, we have y triple prime is equal to x times sine of y. Now, y triple prime, that is our highest derivative, so this one would be considered third order. Okay, and this one is actually nonlinear. And that's because we have that sine of y thrown in there. So we have a function of x times a function of y. And so that kind of throws off our linear form. Okay, so the next section, we have separation of variables. So we're familiar with really simple types of differential equations where we have y prime equals f of x. A solution is simply the antiderivative of f of x. So we've seen this before. Y would equal the integral of f of x dx. A more general class of first order equations that can be solved directly by integration are separable equations, which have the form dy dx is equal to f of x times g of y. Okay, so what you can kind of see here, and this is what we're going to be getting into, is I'm able to move around this equation down here so that my f of x ends up with the dx, and the g of y is going to end up with the dy. And so we'll see some examples on the next page. All right. So the next piece of this, what we're doing is we're actually going to start solving some differential equations. And the way we're going to do this is by separating variables. Now, for this section, we're just finding the general solution, meaning we're not given an initial condition. So you should still have a constant, a c, constant of integration within your solution. Okay, so let's take a look at number 1. Our goal when solving differential equations is we want to get all the x's on one side and all the y's on the other. So first step I'm going to do is add x to both sides. So we have dy dx is equal to x. And then what I can do, now you're not technically multiplying both sides by dx, but it kind of ends up working out like that notation-wise. So we're multiplying both sides by dx. We end up with dy is equal to x dx. Our next step is to integrate both sides. Now, technically, this is 1 dy, so you can even throw a 1 in there as a placeholder. The integral of 1 with respect to y is y. Now, I'm actually going to throw my constant of integration on the other side of the equation. You don't need to have plus c on both. They're technically different c's, so I actually don't even recommend that you put plus c on both because you might cancel them out somewhere on accident. So let's just put it on the other side of the equation. Okay, so the integral of x is 1/2 x squared. And then don't forget that plus c. And so this is it. We have our solution to the differential equation. Dy dx minus x is equal to 0. And the solution is y equals 1/2 x squared plus c. Okay, let's do one more. Let's take a look at number 2. So we have t cubed times y prime plus 4y squared is equal to 0. Our goal is to solve this differential equation in y equals form. Keep in mind your variables here are y and t. So what I'm going to do first is I'm actually going to rewrite y prime as dy dt. Plus, we have 4y squared is equal to 0. Okay, so the next thing I'm going to do is I'm going to subtract 4y squared from both sides. We have t cubed dy dt is equal to negative 4y squared. Now, notice there's a little bit of a problem because the dt is in the denominator and it's with t cubed. And so we want to make sure it's t to the something dt, right? And then y to the something dy. So what we're going to have to do is get a little creative. So what you could do is divide both sides by negative 4y squared. And so what that looks like, or multiply by 1 over negative 4y squared, is you would have 1 over negative 4y squared dy, divide both sides by t cubed, so you have equals 1 over t cubed, right? And then you can divide by dt. So we end up with, multiply both sides by dt. So we end up with 1 over t cubed dt. Now, to make it a little bit easier to integrate, you may want to kind of rewrite these a little bit. So then that way, when you integrate both sides, you can apply those rules pretty easily. So I'm going to pull that negative 1/4 out, and I'm going to rewrite this as y to the negative second dy is equal to the integral of t to the negative third dt. And then I can just apply those integration rules pretty easily. Okay, so once again, I'm going to add my plus c on the side with t. And so that way I don't have to deal with moving things around too much. So I end up with negative 1/4 times, let's see, so we would add 1, then divide by negative 1. So it looks like we'd end up with times negative y to the negative first, which equals, let's see, negative 1/2 t to the negative second plus c. And then let's do a little bit of rewriting just to make this all a little bit nicer and cleaner. So we end up with 1 over 4y is equal to negative 1 over 2t squared plus c. All right, well, now we have a little bit of an issue because we want to make sure that we're in y equals form. So what we could do is we can multiply both sides by y. Okay, so we end up with 1/4 is equal to parentheses negative 1 over 2t squared plus c times y. And then we can just divide both sides to get that y by itself by negative 1 over 2t squared plus c. And so we end up with y, whoops, I'm gonna draw an arrow, y equals 1/4 over negative 1 over 2t squared plus c. And you could simplify that a little bit further, but I'm going to go ahead and leave it as is. Okay, so notice general solution, you should still have a C. Here's a good opportunity to go ahead and pause and try the next two problems on your own. Once you finish them, go ahead and unpause and I will go through them with you. Okay, so hopefully you had a chance to try both of those. What I'm gonna do in this step is notice I have y's and x's, so I'm gonna rewrite y prime as dy dx is equal to y squared times 1 minus x squared. Okay, next thing I'm gonna do is I'm gonna move everything around so I have things in the right spaces. So I'm gonna go ahead and divide by y squared and multiply by dx. Remember, it's multiply by dx. So we end up with 1 over y squared dy is equal to 1 minus x squared dx. Keep that 1 minus x squared in parentheses because you're integrating the whole thing. So be careful with that. Once again, we can rewrite this as the integral of y to the negative second dy, just to make it a little bit easier on ourselves. Up to you. We end up, we can integrate that side already. So the integral of 1 is x minus the integral of x squared is 1/3 x cubed. And then don't forget your plus c. The integral of y to the negative second would be negative y to the negative first, which we could just write as negative 1 over y, which equals x minus 1/3 x cubed plus c. Once again, you do want to make sure that this is in y equals form. And so what you could do is you could multiply both sides like we did before by y. And we end up with negative 1 equals x minus 1/3 x cubed plus c times y, and then divide everything over. And you could keep simplifying, like once again, if this were a multiple choice on the exam, they might have an equivalent answer that looks a little bit different than yours. So you kind of have to play around with how far you go, but for an FRQ, this is perfectly acceptable. You never have to really simplify further than that as long as it's equivalent to that final step on theirs. Okay, so the next thing is number 4. We have dy d theta equals tangent of y. So once again, we need to separate our variables. So we want y's on one side, theta's on the other. So I'm gonna divide by tangent of y and multiply by d theta. So I end up with 1 over tangent of y dy is equal to d theta. Once again, there should kind of be a 1 there as a placeholder. And we're going to integrate both sides. Now, 1 over tangent of y is really just the integral of cotangent of y dy, which equals, we can integrate that theta plus c. Don't forget that plus c. Okay, cotangent of y. Now remember, this is not an integral that you need to memorize. It doesn't really come up on the AP exam, but we did have it down in our notes in a previous lesson. The integral of cotangent of y is the natural log of the absolute value of sine of y, which equals theta plus c. Okay, next what we need to do is we need to solve for y. So what we're going to have to do is we can make each of these e to the power of, right? And so we end up with sine of y is equal to e to the theta plus c. Now we talked about this, how you could actually write this as e to the theta times e to the c. And e to the c is just another constant. Now, it's a good idea to get in the habit of numbering your new constants with subscript. So you could actually rewrite this as sine of y equals e to the c would be my c1 because it's a new constant, right? Times e to the theta. Okay, and then what we do next is we go ahead and we can take the inverse sign of both sides. So it would be y is equal to the inverse sign of c sub 1 e to the theta. And notice that you still have that constant in there. So, okay. So the next page is going to be more problems kind of similar to this, but instead, we are going to be given an initial condition. So that means you actually will have to solve for whatever C is, but the steps are the same. So let's take a look at number 1. First step, we don't actually know what our second variable is, but we can use x dy dx. I always like to rewrite it in this notation because it just makes it that much easier to solve the differentials. Okay. Next, we kind of need to separate our variables. So there's a number of different ways that you can do this, but what I would probably recommend to do is just move the minus 3y and the 12 to the other side. So we'll subtract 12, right, and add 3y to both sides. We end up with dy dx is equal to 3y minus 12. Now we need to make sure everything's on the right side. So I'm going to rewrite this as 1 over 3y minus 12 dy is equal to, right, 1 dx. I'm multiplying both sides by dx. We integrate both sides. Now it's up to you. What you could do here, just because I'm noticing in the denominator there that 3 and 12 have a GCF of 3, you could, to make this a little bit easier, pull out a 1/3, and then you're integrating 1 over y minus 4 dy. And that's completely up to you if you want to do that, is equal to x plus c. Okay, well, the integral of 1 over y minus 4 is equal to 1/3 times the natural log of the absolute value of y minus 4. Now, if you used u sub, you should get the same answer still, and then equals x plus c. Okay, well, I would recommend it's to solve for y first before actually finding c. So let's go ahead and do that. We're going to multiply both sides by 3. We end up with natural log of the absolute value of y minus 4 is equal to 3x plus, now it's 3c, which is just another constant. I'm going to call it c sub 1 because we have a new constant, right? It's kind of that weird constant math that I like to talk about. Okay, the next step is we can raise both to the power of e, or e to the power of, right? And we end up with y minus 4 is equal to e to the 3x plus c1. Now remember, this actually makes the math a little easier. You could rewrite it as e to the 3x times e to the c1 but e to the c1 is just another constant. So we can write that as y minus 4 is equal to c sub 2, new constant, times e to the 3x, and then we add 4. So we have y equals c sub 2 e to the 3x plus 4. But notice this is just the general solution. This isn't the specific one that has y of 2 is equal to 1. So all you have to do to solve for c is plug in 2 for x and 1 for y. I'm going to do that up here because I'm going to run out of space if I don't. So I have 1 is equal to c sub 2, which is what I'm solving for, e to the 3 times x, which is 2, plus 4. We can subtract 4. We end up with negative 3 equals, c sub 2 times e to the 6th, divide by e to the 6th. Now, c sub 2 equals negative 3 divided by e to the 6th. And so what I would, so what I would recommend doing, let's just rewrite this as negative 3 e to the negative 6. It's just going to look a little bit cleaner when we go to plug it in for c. I don't recommend rounding. It's not a good idea. You don't want an approximate solution to these. You want an exact solution. So leave it in exact form. And so your final answer would just be y is equal to negative 3e to the negative 6 times e to the 3x plus 4. And if you wanted to write that in even more simple terms, you could write it as negative 3e to the 3x minus 6, using that exponent rule, plus 4. And so this would be my final answer. So it's just that added extra step of having to go back in and substitute that x and y in that are given to you and solve for c. Okay, so go ahead and take a moment, pause here, try to do those last 3 on your own, and then you can come back and unpause to get the solutions. Okay, so hopefully you had enough time to go through those. Let's look at number 2. So we have y squared dy dx is equal to x to the negative 3rd. This one's not too bad. All we have to do is multiply by dx on both sides. So we have y squared dy is equal to x to the negative 3rd dx. We are going to integrate both sides. We end up with 1/3 y cubed is equal to, now we want to add 1, so we have negative 1/2 x to the negative 2nd plus c. Next step we want to do is multiply both sides by 3. We have y cubed is equal to negative 3/2 x to the negative 2nd. Now it's plus 3c, but you could just write it as c sub 1. It's a new constant. From here, we want to get y by itself, so we're going to cube root both sides. We end up with y is equal to the cube root of negative 3/2 x to the negative 2nd plus c sub 1. You cannot distribute the cube root over addition. It stays like this. It's not the cube root of your first term plus the cube root of the second. That's not equivalent. That is an illegal math move, so please try not to make it. Our last step here is just plugging in our given initial condition, plugging in 1 for x and 0 for y. So we have 0 is equal to the cube root of negative 3/2 times 1 to the negative 2nd plus c sub 1. So we end up with 0 equals the cube root of, just negative 3/2 plus c sub 1. If I cube both sides, it's just 0 equals negative 3/2 plus c sub 1. Add 3/2. And your constant is 3/2. And so our final answer would be y equals the cube root of negative 3/2 x to the negative 2nd plus 3/2. And that is it. Make sure your cube root is long enough. It goes all the way across. Mine was a little short at first. Okay, Last couple, let's take a look at number 3. Okay, so number 3, let's once again rewrite y prime as dy dx is equal to x minus 1 times y minus 2. We want to separate our variables. So we can divide by y minus 2 and multiply by dx. We end up with 1 over y minus 2 dy is equal to x minus 1, keep those parentheses, dx. We can integrate both sides. We end up with the integral of y minus 2, or 1 over y minus 2, is the natural log of the absolute value of y minus 2 is equal to integral of x is 1/2 x squared minus x plus c. Okay, the next thing that we need to do is we need to go ahead and solve for y. So I'm going to have e to the power of, right? We end up with y minus 2 is equal to e to the 1/2 x squared minus x plus c. Now, up to you what you want to do here. I like to rewrite this as y minus 2 equals e to the 1/2 x squared minus x times e to the c, which is really just another constant. So y minus 2 is equal to c sub 1. This is my new constant, e to the 1/2 x squared minus x. All I have to do is add 2, and we have our general solution. Okay, last step, we want to solve for c. So I'm going to plug in 2 for x and 2 for y using that initial condition. Once again, I'm going to move it up here. So we have 2 is equal to c sub 1 e to the 1/2 times 2 squared minus 2 plus 2. Subtracting 2 from both sides, I get 0 equals c sub 1 e to the, let's see, half of 4 is 2 minus 2 is 0. E to the 0 is just 1, so it looks like c sub 1 is equal to 0, which means that the particular solution that we're looking for is actually just y equals 0 times e to the whatever plus 2 is just y equals 2. And when we actually look at the slope fields that represent these differential equations, you'll see sometimes you get linear solutions to something that really looks nonlinear when you look at the general solution. Okay, let's take a look at number 4. We have dy dt is equal to t times e to the negative y. And we're given the initial condition that y of 1 is equal to 0. Okay, so first thing, we need to separate those variables. We can divide by e to the negative y, but keep in mind, 1 over e to the negative y is just e to the y. So it actually worked out fairly nicely for us. Or you can multiply by e to the y on both sides, right? Is equal to, now we multiply by dt, so we get t dt. Go ahead and integrate both sides. We end up with integral of e to the y is just e to the y equals the integral of t is 1/2 t squared. Don't forget about your plus c. Okay, so what you can do next, because we want to solve for y, is we can just take the natural log of both sides. So we end up with y is equal to the natural log of 1/2 t squared plus c. And so from here, we can go ahead and plug in our initial condition to go ahead and solve for c. So I'm going to plug in 0 for y, 1 for t. So we have 0 is equal to natural log of 1/2 of times 1 squared plus c. Okay, so we end up with, you can actually go ahead and raise both sides to the power of e. E to the 0 is just 1 is equal to, you're just left with 1/2 times 1 squared is just a half, plus c, subtract 1/2, and we end up with c is equal to 1/2. So subbing that in, our final answer is y equals the natural log of 1/2 t squared plus 1/2. Okay, and that is all for today's lesson on differential equations and finding both the general and the particular solution when given an initial condition. All right, thanks, guys.